Hello, friend. Welcome back to another quiet journey through the cosmos. Tonight, I want you to imagine something. Right now, at this very moment, light is traveling toward your eyes. Not from your screen, not from the lamp in your room, but from a star so far away that the light left its surface before you were born. If you're 20 years old, that light has been traveling through the void since before you took your first breath. If you're 40, it left when you were still learning to walk. And if you happen to be 80, well, that light began its journey when the world was a different place entirely. The star that sent it is called Alpha Centauri, and it's the closest star to our sun, 4.37 light years away. Our nearest neighbor in the cosmic dark, and yet impossibly unreachably far. Before we drift into this story together, if you find comfort in these quiet explorations of the universe, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. Now, let's drift 4.37 light years. It sounds almost modest, doesn't it? Just 4 years. We measure our own lives in years. 4 years is a college degree, a presidential term, the time it takes a child to grow from newborn to preschooler. But when we say light year, we're not talking about time. We're talking about distance. The distance light travels in 1 year, moving at 186,000 miles per second. Never slowing, never stopping, crossing 7 trillion miles in 12 months. And Alpha Centauri is 4.37 of those journeys away. If you tried to count to 4.37 light years in miles, you'd count 25,280,000,000,000 miles. If you counted one number per second without sleeping, without stopping, it would take you nearly 800,000 years just to count it. The human mind wasn't built for numbers like these. We are creatures of the immediate, the touchable, the seeable. We understand the distance from our bed to the bathroom, from home to work, perhaps from one coast to another. But 25 trillion miles, it becomes abstract, meaningless. Just a number too large to feel. And yet, this is the closest star to us. Everything else, every other point of light you see when you look up at night is farther. Sirius. The brightest star in our sky is 8.6 light years away. Vega, 25. Betelgeuse, somewhere around 540. Though it's so far we can't measure it precisely. The Andromeda Galaxy, our nearest galactic neighbor, is 2.5 million light years distant. If you tried to drive there in a car going 70 miles per hour without traffic, without stopping for gas, it would take you 47 million years just to reach Alpha Centauri, not Andromeda. Alpha Centauri, the close one. There's something quietly devastating about that, isn't there? The nearest star, and it might as well be forever away. Scientists suggest that when ancient humans first looked up and saw the stars, they imagined them as campfires, distant hearths where other beings might sit and wonder at the darkness. Then came the Greeks, who thought perhaps the stars were holes in a great celestial sphere through which divine light poured in. Later, medieval minds believed them to be angels, or the souls of the blessed residing in crystalline spheres that rotated around the earth. It wasn't until the 1600s that we began to suspect the truth, that each star was a sun, that they were not nearby. That distance separated us in ways our ancestors couldn't comprehend. When you look at Alpha Centauri tonight, if you happen to live in the southern hemisphere, where it's visible, you're seeing it as it was 4 years ago. The light entering your eye left that star's surface in 2021 or 2022. It traveled through absolute emptiness, through cold, so complete that temperature barely has meaning, through a void where there is no up or down, no sound, nothing but the light itself and the patient pull of gravity. 4 years of silent travel. And the star you're seeing no longer looks like that. It's already changed subtly, shifted, aged 4 years into a future you won't see for another 4 years. This is what distance does. It turns the present into the past. It makes observation a kind of time travel. Astronomers don't study the universe as it is. They study it as it was. The farther they look, the deeper into history they see. When we observe galaxies billions of light years away, we're watching light that left before Earth existed, before the sun existed. We're seeing a universe that has already changed, already evolved, already moved on. But we won't know what it looks like now until billions of years have passed, if we survive that long, if anything does. Some nights when the concept feels too heavy, I think about the patience of light. It doesn't hurry, it doesn't tire. It doesn't wonder if anyone will be there to see it when it arrives. It simply moves 186,000 miles per second forever. And when it finally reaches your eye 4 years later, it delivers the image of a star exactly as it was, not as you wish it to be, not as it might become, as it was. Truth delayed by distance, but truth nonetheless. Research shows that Alpha Centauri isn't just one star, it's 3, a trinary system locked in gravitational dance. For thousands of years, humans looked up and saw a single point of light. But with telescopes, with measurement, with patience, we learn the truth. What appears as one is actually 2 stars, Alpha Centauri A and Alpha Centauri B, orbiting each other in a slow cosmic waltz that takes 80 years to complete. And orbiting both far out in the dark is Proxima Centauri, a red dwarf so dim it wasn't discovered until 1915. So faint you can't see it with the naked eye, even though it's technically the closest of the 3, the nearest star to Earth, and we didn't even know it was there until a century ago. That's the trick of space. Closeness doesn't mean visible, doesn't mean known. Proxima is just 4.24 light years away, slightly nearer than the other 2. But it's so small, so cool, so dim that even at that distance it barely registers. If our sun is a roaring bonfire, Proxima is a candle flame flickering in a cathedral, present technically, but easily missed. Have you ever stood on a beach at night and looked out at the ocean? The horizon disappears into blackness. You can hear the waves, you can smell the salt, but you can't see where the water ends. You know it's vast, you know ships cross it, but standing there, it feels infinite, unreachable. That's how Alpha Centauri feels to me. I know it's there, I know the numbers, I know the science, but emotionally, experientially, it might as well be in another dimension. 4 light years is close enough to measure and too far to ever truly comprehend. And maybe that's okay. Maybe wonder doesn't require understanding. Maybe knowing something is beautiful and far away is enough. Maybe distance itself is a kind of gift, a reminder that the universe is larger than our needs, our wants, our ability to possess. We can't go there, not yet, maybe not ever, but we can look, we can measure, we can imagine. Light doesn't ask to be understood. It simply arrives patient and constant, carrying images of stars we'll never touch. There's a certain comfort in that, I think, in knowing that long after we're gone, light will still be traveling, stars will still be shining, and somewhere 4.37 years from now, the light leaving Alpha Centauri tonight will reach empty space where Earth once was, and it will keep going, because that's what light does. It moves, it endures, it doesn't need us to witness it. But for now, we're here, and the light is here, and we get to look up and see the past delivered softly to the present. A gift from a star that doesn't know we exist. That's where we begin tonight, with a star so close, it's our neighbor, and so far we may never reach it. With light that traveled for years just to touch your retina for a fraction of a second. With the quiet understanding that some distances aren't meant to be crossed, only admired, only wondered at, only felt. The story of Alpha Centauri isn't just about a star. It's about what happens when we discover something impossibly close and impossibly far at the same time. It's about the moment we realize that even our nearest neighbors might be forever out of reach. It's about distance and time and the strange, beautiful cruelty of a universe built on scales we can measure but never truly feel. But to understand how we got here, how we came to know this star at all, we need to go back. back to a time when the skies were mapped not by machines, but by human eyes. Back to when ancient astronomers first looked south and saw something brilliant hanging low on the horizon, something that would take centuries to truly understand. For thousands of years, humans looked at the same star and saw completely different things. The ancient Greeks called it part of the Centaur. Arab astronomers knew it as Rigil Kentaurus, the foot of the Centaur. Indigenous Australians wove it into dreaming stories about creation and ancestors, and for all of them for millennia, it was one star. Singular, bright, unmistakable. But they were all wrong. What they were seeing wasn't one star at all. It was three hidden in plain sight, waiting for human eyes to grow sharp enough to tell them apart. The discovery didn't happen all at once. It unfolded slowly across centuries as our tools improved and our understanding deepened. And each revelation made the star stranger more complex, more beautiful than anyone had imagined. If you live in the northern hemisphere, you've probably never seen Alpha Centauri. It sits too far south below the horizon for most of North America, Europe, and Asia. For ancient Greek astronomers, it barely cleared the southern horizon, visible only on the clearest nights from the Mediterranean. They included it in their star catalogs, but dimly as an afterthought. Ptolemy listed it in the 2nd century, placing it in the constellation Centaurus, the mythical half-man, half-horse creature. But to them, it was just another point of light, unremarkable compared to Sirius or Vega, or the planets that wandered visibly across the sky. The real observers of Alpha Centauri were those who lived farther south. Indigenous peoples of southern Africa, Australia, and South America saw it not as a footnote, but as a centerpiece of their night sky. To the Burong people of northwestern Victoria in Australia, the star system was part of a larger story about two brothers who hunted emus across the sky. The stars weren't just navigational tools. They were characters and stories that explained the world, the seasons, the movement of animals, the rhythm of life itself. These weren't primitive observations. Research shows that many indigenous astronomical traditions were stunningly precise, tracking stellar positions, planetary movements, and even phenomena like variable stars, long before European science formalized these concepts. But precision and storytelling aren't the same as measurement, and measurement is what eventually revealed the truth. The man who gave Alpha Centauri its modern name was a French astronomer named Abbé Nicolas Louis de la Caille. In 1751, he traveled to the Cape of Good Hope in what is now South Africa. He was 35 years old, physically frail, and suffering from poor health. But he had a mission. He wanted to map the southern skies with the same rigor that northern astronomers had applied to their own hemisphere. For 2 years, he observed nearly 10,000 stars, creating one of the most comprehensive catalogs of the southern celestial sphere ever produced. He worked alone, often through the night, using a small refracting telescope barely more advanced than the ones Galileo had used a century before. Caille didn't discover that Alpha Centauri was multiple stars. That would come later. But he formalized its designation, labeling it Alpha because it was the brightest star in the constellation Centaurus. He measured its position with painstaking care, noting its coordinates, its brightness, its place in the cosmic geography. He treated it with the respect of something significant, even if he didn't yet understand how significant it truly was. He died in 1762 at the age of 46, exhausted, worn down by years of overwork and illness. He never knew that the star he had cataloged so carefully was closer to Earth than almost anything else in the night sky. That revelation came 70 years later, and it came from an astronomer named Thomas Henderson. In 1832, Henderson was appointed His Majesty's astronomer at the Royal Observatory at the Cape of Good Hope, the same place Caille had worked, the same dark skies, the same brilliant southern stars. Henderson wasn't looking for distance initially. He was simply trying to measure stellar positions with greater accuracy. But he had a new tool at his disposal, something Caille never had: the technique of parallax. Parallax is simple in concept, but extraordinarily difficult in practice. Hold your thumb out in front of you and close one eye. Now, switch eyes. Your thumb appears to shift against the background. That shift, that apparent movement, is parallax, and it happens because your two eyes are in slightly different positions. The farther away something is, the less it shifts. If you apply this principle to stars, you can measure their distance. Watch a star at one point in Earth's orbit around the Sun, then watch it again 6 months later when Earth is on the opposite side of its orbit. If the star is close, it will appear to shift very slightly against the more distant background stars. Measure that shift, apply some geometry, and you can calculate how far away it is. In theory, it's elegant. In practice, it's almost impossibly difficult. The shifts are tiny, fractions of a degree, and they require measurements so precise that even the slightest error in your instrument, the slightest atmospheric disturbance, the smallest mistake in calculation will ruin everything. Astronomers had been trying to measure stellar parallax for centuries, and they had failed every single time. But Henderson succeeded. Between April 1832 and May 1833, he meticulously observed Alpha Centauri, measuring its position against the background stars over and over again. He detected a shift, a tiny wobble in the star's position. It was barely there, just 3/4 of an arc second. Imagine a circle divided into 360 degrees. Now divide each degree into 60 arc minutes. Now divide each arc minute into 60 arc seconds. An arc second is 1/3600th of a degree, and Alpha Centauri's parallax was less than 1 arc second. But it was measurable, real, undeniable. Henderson calculated the distance, 4.3 light years, give or take. It was at the time the nearest star ever measured, closer than anything else humanity had found. And yet, even at that proximity, the parallax was almost undetectable. If Alpha Centauri had been any farther, Henderson's instruments wouldn't have been sensitive enough to measure it. He had caught the edge of the possible, the very limit of what 19th century technology could achieve. But here's the strange part. Henderson didn't publish his findings immediately. He sat on the data for years. Some historians suggest he doubted himself. The measurement was so small, the implications so enormous that he may have feared being wrong. Or perhaps he simply didn't realize what he had found. He was a careful man, methodical, not prone to grand announcements. By the time he finally published in 1839, another astronomer, Friedrich Bessel, had already announced the parallax of a different star, 61 Cygni. Bessel got the credit for being first. Henderson's discovery, though technically accurate and arguably more significant, was overshadowed. He died just 3 years later in 1844, 46 years old, the same age Lacaille had been, worn down by overwork and illness. Another life, consumed by the stars. But the story doesn't end there, because even Henderson, even with his precise measurements, was still looking at Alpha Centauri as a single star. It wasn't until later in the 1800s that astronomers realized it was actually 2 stars orbiting each other, Alpha Centauri A and Alpha Centauri B, so close together that to the naked eye, even through most telescopes, they appear as one. Only with high magnification and steady atmospheric conditions can you see them separately. 2 points of light, golden and amber, circling each other in a dance that takes 80 years to complete. And then came the third. In 1915, a Scottish astronomer named Robert Innes was studying photographic plates taken at the Union Observatory in South Africa. He noticed something odd, a faint red star barely visible that seemed to be moving across the sky at an unusually high rate. High proper motion, as astronomers call it. Stars that move quickly across the sky relative to the background are usually close to us. The farther away a star is, the less it appears to move, because it's so distant that even vast actual motion translates into almost no observable shift from our perspective. But this little red star was zipping along at 3.85 arc seconds per year. That might not sound like much, but in astronomical terms, it's a sprint. Innes calculated its distance, 4.24 light years, closer than Alpha Centauri A and B, closer than anything, the nearest star to Earth, and we had missed it for all of human history. He named it Proxima Centauri, Proxima meaning nearest. And it was so dim, so faint, so unremarkable that even though it was the closest star in the universe to us, you cannot see it without a telescope. It glows with just 1/600th the luminosity of our sun, a dying ember compared to the roaring furnace of Alpha Centauri A. Think about that for a moment. The closest star to Earth is invisible to the naked eye, our nearest neighbor, and it took us until 1915 to even notice it existed. How many other things are hiding in plain sight too dim or too distant or too strange for us to detect? How much of the universe are we still missing? Not because it's far away, but because we simply don't have the eyes to see it. Yet there's a lesson in that, I think. Discovery isn't always about looking farther. Sometimes it's about looking closer, more carefully, with better tools and sharper attention. The Greeks saw one star. Henderson measured one star. But the truth was 3 stars all along. We just needed time, patience, and the humility to realize we might be wrong about what we thought we knew. Alpha Centauri taught us that closeness doesn't mean simplicity, that even our nearest neighbors can hide layers of complexity, that what appears singular might be multiple, what seems simple might be intricate, what looks understood might still hold secrets, and the secrets keep unfolding. Because once we knew there were 3 stars, we started asking a different question, a question that would consume the next century of astronomical research. If there are 3 stars so close to us circling each other in gravitational harmony, what else might be there? What else might be hidden in that system, too small or too dark or too far out to see? Could there be planets? Could there be worlds? Could there just maybe be something like Earth orbiting our nearest stellar neighbor, close enough to almost touch? That question, simple and profound, would drive scientists to build bigger telescopes, smarter instruments, more sensitive detectors. It would lead to campaigns with poetic names like Pale Red Dot to Sleepless Nights, analyzing data to the slow, patient work of watching a star for the tiniest wobble that might betray the presence of something unseen. And what they found when they finally looked closely enough was stranger and more tantalizing than anyone had imagined. 3 stars bound together by gravity, spinning through space in patterns so complex that even now, centuries after their discovery, we're still mapping the choreography. Alpha Centauri isn't a star, it's a performance, a gravitational ballet that's been playing out for billions of years, long before there were eyes to watch it, and will continue long after we're gone. Imagine trying to predict where 3 dancers will be in 80 years when each one's movement depends on the position of the other 2, and all 3 are moving at speeds we can barely comprehend. That's what astronomers face when they study Alpha Centauri. Not one predictable orbit, but 3 bodies locked in mutual influence, pulling and tugging and swaying in ways that require supercomputers to model accurately. The 2 main stars, Alpha Centauri A and B, are what scientists call a binary pair. They orbit a common center of gravity, a point in empty space between them, where their combined mass balances perfectly. Neither star is stationary. Both are falling toward that invisible point, and both are moving fast enough that they never quite reach it. It's like 2 people holding hands and spinning in circles. Neither is the center. The center is the space between them, and they both revolve around it, held together by the grip of gravity instead of fingers. Alpha Centauri. A is the larger of the 2. Scientists classify it as a G-type main sequence star, the same category as our Sun. But it's not identical. It's about 10% more massive, 23% wider in diameter, and it burns about 52% brighter. If you could stand on a planet orbiting Alpha Centauri A at the same distance Earth orbits our sun, the star would feel noticeably hotter, the light slightly more intense. Not enough to make life impossible, but enough that you'd feel the difference. Summers would be hotter, winters less forgiving. The habitable zone, that sweet spot where liquid water can exist on a planet's surface, would be pushed a little farther out. Alpha Centauri B is smaller. It's a K-type orange dwarf, cooler and dimmer than its companion. It has about 90% the mass of our sun and shines with only 45% of its luminosity. If our sun is a cheerful yellow Alpha Centauri, B is a warm amber, less intense, gentler, but still a star. Still a nuclear furnace fusing hydrogen into helium at its core, still pumping out heat and light and radiation into the void. The two stars circle each other once every 79.91 years, just shy of 80 Earth years. Their orbit isn't circular, it's elliptical, stretched into an oval shape, which means the distance between them changes dramatically over the course of their dance. At their closest approach, called periastron, they're separated by about 11 astronomical units. An astronomical unit, or AU, is the distance from Earth to the Sun, roughly 93 million miles. 11 AU is about the distance from our Sun to Saturn. So at their closest Alpha Centauri, A and B are as far apart as Saturn is from us. That might sound distant, but remember, these are stars, not planets. Imagine if Saturn were a star as bright as the Sun. The sky on Earth would never truly be dark. We'd live in a world of perpetual twilight, one sun setting as the other rose. At their farthest separation, called a pastron, the two stars drift out to about 35.6 astronomical units. That's roughly the distance from the Sun to Pluto. Even at this distance, they're still bound together. Gravity doesn't weaken quickly. It falls off with the square of the distance, which means doubling. The distance reduces the gravitational force by a factor of 4, but it never reaches 0. No matter how far apart they drift, they're still pulling on each other, still locked in their mutual orbit. Scientists suggest that if you were standing on a planet orbiting Alpha Centauri, a Alpha Centauri B would be the brightest object in the night sky by far. At closest approach, it would shine with the light of more than 100 full moons, bright enough to cast shadows, bright enough to read by. You wouldn't need streetlights. The companion star would do the job just fine. And at farthest separation, it would still be brighter than Venus appears from Earth. Always there, always watching. A second sun that never set, just dimmed and brightened on an 80-year cycle. But the dance doesn't stop with two. There's a third partner moving to a different rhythm entirely. Proxima Centauri, that dim red dwarf discovered in 1915, doesn't orbit the binary pair in any simple way. Its orbit is so vast, so elongated, so profoundly eccentric that astronomers spent decades arguing over whether it was even gravitationally bound to Alpha Centauri A and B at all. Maybe it was just passing by a visitor that happened to wander close and would eventually drift away into the dark. But research conducted over the past few decades strongly suggests it's not a visitor. It's part of the family, a distant, quiet member of the system, bound by gravity but separated by enormous distance. Proxima orbits the central binary at a distance of roughly 13,000 astronomical units. To put that in perspective, Neptune, the farthest planet in our solar system, orbits at 30 astronomical units. Proxima is more than 400 times farther from Alpha Centauri, A and B, than Neptune is from the Sun. At that distance, the two central stars would appear bright, yes, but not as suns. They'd look like very bright stars close together, far brighter than anything else in the sky, but clearly distant, separate, cold. The orbital period is staggering. Scientists estimate Proxima takes about 550,000 years to complete one full orbit around the binary pair. 550,000 years. Modern humans, Homo sapiens have only existed for about 300,000 years. Proxima hasn't even completed one full orbit since our species emerged. It's been swinging through space on a journey so long that entire civilizations could rise and fall in the time it takes to loop around just once. And here's the fascinating, slightly unsettling part. Proxima's orbit brings it as close as 4,300 astronomical units to the binary pair and as far as 13,000 astronomical units away. Right now, it's near its closest approach. In about 27,000 years, it will reach Periastron, the point where it's closest to Alpha Centauri A and B. Then it will begin drifting outward again, slowly, patiently over the next 250,000 years. By the time it swings back around, if humanity still exists, we'll be so different we might not even recognize ourselves. Do you ever think about the time scales involved in these cosmic dances? 80 years for the binary pair, 550,000 years for Proxima, and all of it happening in what we consider our cosmic neighborhood. The closest stars to us and their movements unfold over time scales that dwarf human history. There's a common mistake people make when they think about star systems. They imagine them as static, fixed points of light, unchanging and eternal, but nothing in space is still. Everything moves. Stars orbit galaxies. Galaxies drift through the universe. And within systems like Alpha Centauri, the stars themselves are in constant motion, bound by gravity, following paths determined billions of years ago when the system first formed. Research shows that Alpha Centauri AB and Proxima likely all formed from the same molecular cloud around 4 to 6 billion years ago. They're siblings born together, even if Proxima ended up as the runt of the family. Over time, gravitational interactions between the three may have changed. Proxima might have once orbited closer, or maybe it was captured later, pulled in by the gravity of the binary pair from a nearby region of space. We don't know for certain. What we do know is that now today they're bound together, a trinary system, 3 stars, 3 wildly different personalities locked in a gravitational relationship that will last for billions of years more. If our sun were a tennis ball, Alpha Centauri, A would be a slightly larger tennis ball, maybe the size of a softball. Alpha Centauri B would be just a bit smaller than a tennis ball. And Proxima would be a marble, a small, dim reddish marble. And if the sun were a tennis ball sitting in New York City, Alpha Centauri would be another set of balls sitting in Los Angeles. That's the scale we're dealing with. Thousands of miles separating objects that are cosmically speaking neighbors. The gravitational dance between these 3 stars creates zones of stability and instability within the system. There are regions where planets can form and survive, and regions where the competing gravitational pulls would tear them apart or fling them into interstellar space. For decades, scientists debated whether planets could even exist in such a chaotic environment. Would the gravitational tug-of-war destroy any forming worlds before they had a chance to coalesce? Or could planets find stable orbits tucked into gravitational safe zones, orbiting one star while the others pulled from a distance? The answer, as we would eventually discover, is yes. Planets can exist. They do exist. But finding them required patience, precision, and technology that didn't exist until very recently. One of the key challenges is that Alpha Centauri A and B are so close together and so bright that their light drowns out anything orbiting them. Imagine trying to spot a firefly hovering next to a searchlight from 1,000 miles away. That's what it's like trying to see a planet next to a star. The star is millions or billions of times brighter. The planet, if it reflects any light at all, is lost in the glare. So astronomers had to get clever. They couldn't see the planets directly, but they could detect the subtle effects planets have on their stars. When a planet orbits a star, it doesn't just move around the star. Both the planet and the star orbit their common center of mass. For a massive star and a tiny planet, that center of mass is very close to the star's center, but not exactly at the center. So the star wobbles, just a little. A tiny back and forth motion. caused by the planet's gravity tugging on it. If you measure the star's light precisely enough, you can detect this wobble. The star will shift slightly toward you, compressing its light and making it appear very slightly bluer. Then it will shift away, stretching its light and making it appear very slightly redder. This is called the radial velocity method, and it's how we've found thousands of exoplanets. But it requires incredibly sensitive instruments. The wobble caused by an Earth-sized planet is minuscule. We're talking about changes in velocity of a few meters per second, walking speed, and you have to detect that across 4 light-years of space. For Alpha Centauri, the challenge was even greater. The 2 stars orbit each other, which creates its own wobbles. You have to account for that motion, subtract it out, and then look for the even smaller wobbles that might indicate a planet. It's like trying to hear a whisper in a room full of people talking. You have to filter out all the noise, all the competing signals, and isolate the one tiny voice that might be there. But scientists tried. They watched Alpha Centauri A and B for years, measuring their spectra, analyzing their light, searching for patterns. And eventually, they found something. Not around the binary pair, but around the 3rd star, the distant one, the dim red marble orbiting in the outer dark. Proxima Centauri, our closest stellar neighbor, turned out to be hiding worlds of its own. And those worlds would challenge everything we thought we knew about where life could exist. There's a planet orbiting the closest star to Earth, a rocky world slightly larger than our own, sitting in what astronomers call the habitable zone, the region where temperatures might allow liquid water to exist on the surface, where life in theory could take hold. It's 4.2 light-years away, the nearest potentially habitable planet we've ever found. And it might be one of the most hostile, radiation-scorched, uninhabitable places in the galaxy. The universe has a cruel sense of irony sometimes. The search for planets around Proxima Centauri wasn't driven by idle curiosity. It was driven by hope. If our nearest stellar neighbor had planets, especially planets in the habitable zone, it would change everything. It would mean that Earth-like worlds might be common, that we weren't alone in our capacity to host life, and it would give us a target, a destination. Something close enough that interstellar travel, while still impossibly difficult, might at least be theoretically achievable within the span of human lifetimes if we develop the right technology. So, in January 2016, a team of astronomers launched a campaign called Pale Red Dot. The name was a deliberate echo of Pale Blue Dot, the famous photograph of Earth taken by Voyager 1 from the edge of the solar system. That image showed our planet as a tiny speck, suspended in a beam of sunlight, fragile and alone. The Pale Red Dot campaign hoped to find something similar around Proxima Centauri, a pale dot. Red because Proxima is a red dwarf star, and any planet reflecting its light would have a reddish tint. A world that might be capable of supporting life. The campaign used the HARP spectrograph at the Lucia Observatory in Chile. HARP stands for High Accuracy Radial Velocity Planet Searcher, and it's one of the most sensitive planet hunting instruments ever built. It measures the tiny wobbles in a star's motion, caused by the gravitational pull of orbiting planets. The principle is simple. When a planet orbits a star, the star doesn't stay perfectly still. It wobbles ever so slightly as the planet's gravity tugs on it. By measuring the star's spectrum, astronomers can detect shifts in the wavelength of light caused by this motion. When the star moves toward us, its light is compressed, shifted toward the blue. When it moves away, the light is stretched, shifted toward the red. This is the Doppler effect, the same phenomenon that makes a siren sound higher pitched as an ambulance approaches and lower pitched as it drives away. For a planet the size of Earth orbiting a star like Proxima Centauri, the wobble is minuscule. We're talking about velocity changes of about 1.4 meters per second. That's walking speed. Imagine trying to measure whether someone in Los Angeles is walking toward you or away from you while you're standing in New York, and they're only moving at walking speed. That's the level of precision required, and you have to do it across 4 light-years of space through the distortion of Earth's atmosphere while accounting for the star's own variability and every other source of noise in the data. The Pale Red Dot campaign observed Proxima Centauri almost every single night for 3 months. Nights when the weather was bad, they didn't get data. Nights when the moon was too bright, the observations were less reliable. But slowly, patiently, the data accumulated, and a pattern emerged. The star was wobbling. Not much, just enough. And the wobble had a rhythm, an 11.2-day cycle. That meant something was orbiting Proxima Centauri, once every 11 days, pulling on the star, causing it to sway back and forth in response. The team calculated the planet's mass, at least 1.17 times the mass of Earth. A rocky world, almost certainly. Too small to be a gas giant, too large to be a moon. It was a planet, and it was close. Scientists suggest that Proxima b, as the planet was named, orbits its star at a distance of just 0.048 astronomical units. That's about 7.5 million kilometers, less than 5 million miles. For comparison, Mercury, the closest planet to our Sun, orbits at 0.39 astronomical units, more than 8 times farther. Proxima b is close, incredibly close. If it were orbiting our Sun at that distance, it would be well inside the orbit of Mercury, scorched to a lifeless cinder by the Sun's heat. But Proxima Centauri isn't our Sun. It's a red dwarf, much cooler and dimmer. It only produces about 0.17% of the Sun's luminosity. So even though Proxima b orbits very close, it receives only about 65% of the radiation that Earth gets from the Sun. That puts it squarely in the habitable zone. Not too hot, not too cold. Temperatures where liquid water could in theory exist on the surface. The announcement in August 2016 sent ripples through the scientific community and captured public imagination. Headlines proclaimed the discovery of a potentially habitable planet around our nearest star, a neighbor world, a second Earth practically on our doorstep. The dream of finding life beyond our solar system suddenly felt tangible, real, close enough to almost touch. But then the reality set in. Proxima Centauri is not a gentle star. Red dwarfs are small, yes, and dim compared to stars like our Sun. But they're also violent, unpredictable, prone to massive stellar flares that can increase their brightness by factors of 10 or even 100 in a matter of minutes. These flares release tremendous amounts of high-energy radiation, ultraviolet light, X-rays, charged particles that stream out into space like solar tsunamis. Research shows that Proxima Centauri experiences major flares several times per year. In March 2017, just months after the discovery of Proxima b was announced, astronomers observed a flare that increased the star's brightness by 1,000 times in the ultraviolet spectrum. For 10 seconds, Proxima Centauri shone with the ultraviolet intensity of a much larger, hotter star. The radiation released in those 10 seconds was equivalent to a substantial fraction of what our Sun releases over an entire year. Now, imagine you're standing on the surface of Proxima b. Your Sun, normally a dull red ember in the sky, suddenly blazes with deadly radiation. Ultraviolet light floods the landscape. If the planet has an atmosphere, the flare could strip away chunks of it, molecule by molecule, blown into space by the force of the stellar wind. If the planet has a magnetic field, it might deflect some of the radiation. But red dwarf flares are so intense that even a magnetic field might not be enough. And if the planet doesn't have a magnetic field, if it's tidally locked with one side always facing the star, the surface would be bathed in radiation over and over again, year after year, for billions of years. Scientists estimate that Proxima b receives about 250 times more X-ray radiation than Earth does. 250 times. That's not a hospitable environment. That's a radiation bath. There's another problem, tidal locking. Because Proxima b orbits so close to its star, and because Proxima Centauri is relatively massive compared to the planet, Gravitational forces have likely locked the planet's rotation to its orbit. One side of the planet always faces the star, eternal day. The other side always faces away, eternal night. The day side might be scorching hot. The night side might be frozen solid. The only potentially habitable region would be the terminator, the narrow band between day and night, where temperatures might be moderate enough for liquid water. But even there, the temperature difference would drive ferocious winds, storms of unimaginable violence as air rushes from the hot side to the cold side and back again in an endless atmospheric loop. Does life stand a chance in a place like that? We don't know. Life on Earth has survived in some truly extreme environments. Deep-sea hydrothermal vents where temperatures exceed boiling. Antarctic ice where organisms eke out existence in microscopic pockets of liquid water. Caves sealed off from sunlight for millions of years. Deserts where it hasn't rained in decades. Life is tenacious. It adapts. But there's a difference between thriving and merely surviving. And there's a difference between harsh and outright hostile. Even if Proxima b once had oceans, the relentless stellar flares might have boiled them away billions of years ago. Even if it had an atmosphere, the radiation might have stripped it down to a thin wisp, unable to retain heat or protect the surface from cosmic rays. The planet might be a barren rock, dry and dead, irradiated beyond recognition. Or it might surprise us. It might have held on, developed a thick atmosphere, a strong magnetic field, some mechanism we haven't thought of yet to shield itself from the fury of its star. We simply don't know, and we won't know until we can observe the planet more directly. Which brings us to the next challenge. Proxima b doesn't transit its star from our perspective. That means it doesn't pass in front of Proxima Centauri as seen from Earth. We can't watch it block a tiny fraction of the star's light and analyze that light to determine what's in the planet's atmosphere. The technique that's revealed so much about other exoplanets doesn't work here. We're stuck with indirect methods, measuring the wobble of the star, waiting for better telescopes, hoping for a lucky break. But Proxima b wasn't the only world they found. In 2019, analysis of additional data revealed hints of a second planet, Proxima c. This one is farther out, orbiting at about 1.5 astronomical units, roughly the distance of Mars from our Sun. It's larger, with a minimum mass of about 6 times that of Earth. Too big to be rocky. Likely a mini Neptune or a super-Earth with a thick gaseous envelope. And it's cold, far outside the habitable zone. Temperatures where water would be frozen solid if it exists at all. Then, in 2022, came Proxima d, a third planet, this one even closer to the star than Proxima b. It orbits every 5 days at a distance of just 0.029 astronomical units, less than 4.5 million kilometers. And it's tiny, only about 1/4 the mass of Earth. The smallest planet ever detected using radial velocity measurements. A world so close to its star that it's likely tidally locked, baked on one side, and frozen on the other, far too hot to support life as we know it. 3 planets, orbiting our nearest stellar neighbor, a system more complex than anyone expected. And each planet tells us something different about how worlds form, how they survive, how they endure in the violent environment of a red dwarf star. There's a term astronomers use when they talk about planets like Proxima b. They call them worlds in the habitable zone, but they're careful not to call them habitable. The habitable zone is just a distance range, a geometric convenience. It's the region where, if conditions are right, liquid water might exist. But conditions are rarely right. You need an atmosphere, but not too thick. A magnetic field, but strong enough to matter. A stable climate, but not so stable that it's frozen or boiling. You need the planet to form with enough water in the first place to avoid too many asteroid impacts that could sterilize the surface, to have a star that doesn't flare too often or too violently. The habitable zone is necessary for life, but it's nowhere near sufficient. It's like saying a house is in a good neighborhood. That doesn't mean it's livable. It doesn't mean the roof doesn't leak. or the foundation isn't cracked. It just means the address is promising. So, when we talk about Proxima b as a potentially habitable world, we're being hopeful, optimistic, but we're also being realistic. The odds are not in that planet's favor. The odds are that it's dead, dry, irradiated. A cautionary tale about the dangers of living too close to a violent star. But there's a small chance, a whisper of possibility, that maybe life found a way, that something is clinging to existence on that pale red dot 4 light years away, waiting for us to notice it. And that possibility, however slim, is enough to keep us looking, enough to justify building better telescopes, designing new instruments, spending years analyzing data, in the hope of finding some sign, some signal, some proof that we're not alone. Because if life exists on Proxima b, the closest potentially habitable planet we know of, then the universe might be teeming with life. And if even that nearby world is too harsh, too hostile, too broken to support biology, then maybe Earth is more precious than we realize. Maybe we're not just rare. Maybe we're impossibly lucky. The question is whether luck alone is enough to carry life across the vast, cold distances between the stars. If you started driving right now at a highway speed, never stopping for gas or sleep, or food, driving in a perfectly straight line through the vacuum of space, it would take you 47 million years to reach Alpha Centauri. Your great-great-great-grandchildren, thousands of generations removed, would still be driving. The car would have turned to dust and reformed into new matter multiple times. Species on Earth would have evolved and gone extinct. And you still wouldn't be there. 4.37 light years sounds close. It sounds manageable, a handful of years, a presidential term, a college degree. But when you try to cross it, when you actually attempt to translate that distance into human terms, into speeds and times and journeys, we can understand it stops being a number and becomes something else entirely, an abyss, a gulf so vast that our fastest machines, our most advanced technology, our wildest dreams of propulsion barely make a dent in it. Let's start with what we've actually built. The fastest human-made object currently traveling through space is Voyager 1. Launched in 1977, it's been flying for nearly 50 years now. It's crossed the boundary of our solar system, entered interstellar space, and it's still moving. Still transmitting data, though faintly, from more than 15 billion miles away. Its speed relative to the sun is about 38,000 miles per hour. That's roughly 17 kilometers per second. 17,000 meters every second. Fast enough to cross the continental United States in about 4 minutes. And at that speed, it would take Voyager 1 about 73,000 years to reach Alpha Centauri. 73,000 years. Longer than recorded human history. Longer than agriculture has existed. Longer than cities writing metallurgy, any of the technologies we think of as foundational to civilization. If you had launched Voyager 1 toward Alpha Centauri at the end of the last ice age, when humans were still hunter-gatherers living in small nomadic bands, it would only just now be arriving. But Voyager 1 isn't even heading toward Alpha Centauri. It's pointed in a completely different direction, out toward the edge of the galaxy, wandering into the dark with no particular destination. It will drift for millions of years, maybe billions, until it eventually falls into the gravity well of some distant star we've never heard of. A ghost ship carrying a golden record engraved with sounds and images of Earth, a message in a bottle thrown into an ocean so vast that it will almost certainly never be found. Let's try something faster. The Parker Solar Probe, launched in 2018, holds the record for the fastest speed ever achieved by a human-made object. At its closest approach to the Sun, it reaches speeds of about 430,000 miles per hour. That's 192 kilometers per second. It's moving so fast that if it were traveling toward Alpha Centauri at that speed, it would get there in about 6,700 years. Still impossibly long. still far beyond the span of any human civilization that's ever existed. But better, a little closer to the edge of conceivable, except the Parker Solar Probe can't maintain that speed. It only reaches those velocities when it's falling toward the sun, accelerated by gravity, whipping around in a slingshot maneuver before flying back out. Once it's far from the sun, it slows down. And more importantly, it's not designed to leave the solar system. It's designed to study the sun's corona, to fly closer to our star than anything has before, and then come back for another pass. It's not going anywhere. It's circling like a moth around a flame. Scientists suggest that if we wanted to send something to Alpha Centauri within a human lifetime, we'd need to achieve speeds of at least 10 to 20% the speed of light. The speed of light is about 186,000 miles per second, 300,000 kilometers per second. At 10% of that, you'd be moving at 18,600 miles per second, 30,000 kilometers per second. At that speed, you could circle the Earth in about 1.3 seconds. You could reach the moon in about 13 seconds. You could cross the distance from Earth to the sun in about 8 minutes. And at 10%, the speed of light, you could reach Alpha Centauri in about 43 years. Not fast, but achievable within a human lifetime. Someone who left Earth at age 20 might arrive at age 63. Old, yes, but alive, conscious, able to see the destination, to experience the arrival, to send back data images, proof that we made it. But here's the problem. We have no idea how to build something that can travel at 10% the speed of light. None. Not even close. Our fastest spacecraft reach about 0.02% the speed of light. We're off by a factor of 500. It's not a matter of incremental improvement. It's not like going from a propeller plane to a jet engine. It's a fundamental technological gap, a chasm we don't yet know how to cross. Let's put this in perspective. Imagine you're trying to throw a baseball from New York to Los Angeles. That's roughly 2,400 miles. A professional pitcher can throw a baseball at about 100 miles per hour. At that speed, the ball would take 24 hours to reach Los Angeles, assuming it could somehow maintain its velocity and didn't fall to the ground. Now, imagine you need to throw the baseball to the moon, which is about 239,000 miles away. At 100 miles per hour, that would take about 99 days. Now imagine you need to throw it to the sun, 93 million miles away. That would take about 106 years. And now, imagine you need to throw it to Alpha Centauri 25 trillion miles away. That would take about 28 million years. That's the scale we're dealing with. And we're not throwing baseballs. We're trying to send machines that need power guidance communication systems, scientific instruments, shielding from radiation and micrometeorites. Machines that weigh something that require fuel or some other form of propulsion that can't just coast forever without eventually breaking down. Research shows that the energy required to accelerate even a small spacecraft to a significant fraction of the speed of light is staggering. If you wanted to accelerate a 1-ton spacecraft to 10% the speed of light, you'd need about 450 trillion joules of energy. That's roughly the total energy consumption of the entire United States for about 3 hours, just to accelerate. Not to slow down when you get there, not to power the spacecraft during the journey, not to transmit data back to Earth, just to get it moving. And where does that energy come from? Chemical rockets won't work. The amount of fuel you'd need would be so enormous that the spacecraft would be too heavy to accelerate efficiently. You'd need more fuel to carry the fuel, and more fuel to carry that fuel in an exponential spiral that quickly becomes absurd. The Tsiolkovsky rocket equation, formulated in the late 1800s, put strict limits on how fast you can go with chemical propulsion. And those limits are nowhere near what we need for interstellar travel. What about nuclear propulsion? That's more promising. Fission or fusion reactions release far more energy per unit of mass than chemical reactions. A nuclear rocket could in theory achieve much higher velocities. But even nuclear propulsion has limits. You still need to carry fuel. You still need to deal with the heat generated by the reactions, the radiation, the mechanical stresses. And you still don't get anywhere close to 10% the speed of light with current designs. Some scientists have proposed using antimatter as fuel. When matter and antimatter collide, they annihilate each other and convert their entire mass into energy, according to Einstein's famous equation, E equals mc squared. It's the most efficient energy release possible. A single kilogram of antimatter colliding with a kilogram of matter would release about 90 quadrillion joules of energy, enough to power the entire United States for more than 2 years. But there's a small problem. We can't make antimatter in any meaningful quantity. The total amount of antimatter ever produced by humanity is measured in nanograms, billionths of a gram. It would take tens of thousands of years to produce even a single gram at current production rates, and we have no way to store it. Antimatter annihilates instantly upon contact with normal matter, which means you'd need some kind of magnetic containment system that never ever fails. One glitch, one power fluctuation, and your fuel supply explodes with the force of multiple nuclear weapons. So, antimatter, while theoretically ideal, is practically useless, at least for now. There's another approach. Instead of carrying fuel, what if you push the spacecraft from behind with a powerful laser? This is the concept behind light sails, also called photon sails. You build a spacecraft with a huge thin reflective sail. Then you aim an enormously powerful laser at it from Earth. The photons from the laser hit the sail and transfer momentum, pushing the spacecraft forward. No fuel needed on the spacecraft itself. All the energy comes from the laser on Earth. It's elegant, in theory. But the engineering challenges are immense. The laser would need to be incredibly powerful, on the order of gigawatts, or even tens of gigawatts sustained for minutes or hours. That's more power than most countries generate at any given moment. And the laser would need to stay focused on a sail that's getting farther away every second, eventually millions or billions of miles distant. Even a tiny error in aim, a fraction of a degree, and the laser beam would miss entirely. You'd also need the sail to be enormous and incredibly lightweight. We're talking about sails hundreds or thousands of meters across, made of materials that can withstand the intense heat of a gigawatt laser without vaporizing. And even if you solve all those problems, you face another issue. How do you slow down when you get there? The laser is back on Earth. It can't decelerate you. So either you accept that your spacecraft is going to fly past Alpha Centauri at a significant fraction of the speed of light, giving you only a brief window to collect data as you scream through the system, or you need some way to brake. Maybe another laser at the destination, which means you'd have to send a second mission ahead of time to build the laser infrastructure. Or maybe you detach part of the sail and use it as a brake, reflecting light from Alpha Centauri itself to slow down. But that requires even more mass, more complexity, more things that can go wrong. Do you ever think about how much we take for granted when we talk about space travel? We imagine sleek ships gliding between the stars like they do in movies. Smooth, effortless, quick. But the reality is brutal. Space is empty, yes, but it's not safe. Cosmic rays, high-energy particles from distant supernovae, and other violent cosmic events stream through space constantly. On Earth, we're protected by our atmosphere and magnetic field. In space, those particles tear through you, damaging DNA, increasing cancer risk, degrading electronics. A spacecraft traveling at high speed would smash into interstellar hydrogen atoms, and even though space is mostly empty at relativistic speeds, those tiny atoms hit with the force of bullets. You'd need shielding, heavy shielding, which adds mass, which requires more energy to accelerate. Then there's the cold. Space is about 2.7 Kelvin, just a few degrees above absolute zero. Any spacecraft needs to maintain operable temperatures for its electronics and instruments, which means heaters, which means power, which means either solar panels that become useless once you're far from the sun, or nuclear reactors, which add mass and complexity, and communication. At 4 light-years away, every message you send takes 4 years to reach Earth. Every response takes another 4 years to come back. 8 years round trip. You can't have a conversation. You can't troubleshoot problems in real time. If something goes wrong, the people on Earth won't even know about it until 4 years after it happened. And by the time they send a solution, another 4 years will have passed. The spacecraft has to be autonomous, self-repairing, intelligent enough to handle the unexpected. And we've never built anything like that for a mission of this duration. There's a harsh truth here, one that science fiction often glosses over. Interstellar travel isn't just hard. It's not just expensive. It's not just beyond our current technology. It might be fundamentally incompatible with the kind of beings we are. We live for decades, not centuries. We need food, water, air, gravity, protection from radiation. We get bored, lonely, depressed. We make mistakes. We die, and space doesn't care. It doesn't adjust to our needs. It simply is what it is, vast and cold and indifferent. And if we want to cross it, we have to change ourselves, or accept that maybe it's not meant to be crossed. Not by us, not in the bodies we have, not in the lifetimes we're given. Alpha Centauri sits there close enough to measure too far to reach a reminder that the universe operates on scales we weren't built for. But knowing the scale, feeling the weight of that impossible distance doesn't stop us from trying. It never has. Because humans are strange like that. We dream of things we can't have, and then we spend centuries trying to make the impossible real. In 1968, a group of physicists sat down and seriously calculated how to build a spaceship propelled by nuclear bombs, not as a weapon, as transportation. They called it Project Orion, and on paper it could have worked. You detonate atomic bombs behind a massive steel plate one after another, each explosion pushing the ship forward. Boom, boom, boom. A controlled series of nuclear detonations riding the shockwave to the stars. The math checked out. The physics was sound. It was utterly insane, and it was one of the most serious proposals for interstellar travel ever conceived. The dream of reaching Alpha Centauri didn't start with modern technology. It started with dreamers, people who looked up at the stars and refused to accept that distance was permanent. That 4 light-years might as well be forever. They sketched designs on napkins, filled blackboards with equations, published papers that mixed rigorous science with wild optimism. Most of their ideas never left the drawing board. Some were genuinely brilliant. A few were completely unhinged. But all of them shared one thing: the belief that if we wanted it badly enough, if we thought hard enough, we could find a way. Project Orion began in 1958 at General Atomics in San Diego. The lead physicist was a man named Ted Taylor, brilliant and eccentric, someone who thought in terms of mega-scale engineering. The idea was simple in concept. Nuclear bombs release enormous amounts of energy in a very short time. If you could harness that energy directed, you could accelerate a spacecraft to incredible speeds. The design called for a massive shock absorber plate at the back of the ship. You'd eject a nuclear bomb behind the ship, detonate it, and the explosion would hit the plate, transferring momentum. The plate was connected to the rest of the ship through huge hydraulic shock absorbers that would smooth out the impulse, turning a violent explosion into steady acceleration. The engineers calculated that a large Orion spacecraft weighing thousands of tons could reach Mars in a month, Saturn in 7 months. And with enough bombs, enough mass, you could potentially reach a few % of the speed of light, which would put Alpha Centauri within reach in maybe a century or two. Not fast enough for a single human lifetime, but fast enough that a generation ship might make the journey. Research shows that the engineers working on Orion were deadly serious. They built scale models. They conducted tests with conventional explosives to prove the concept. In 1959, they actually detonated small charges beneath a 1-meter test vehicle and watched it fly. It worked. The ship lifted off, stabilized, and landed intact. The physics wasn't theoretical. It was real. You could ride nuclear explosions to space, but Orion had problems, massive problems. First, there was the radiation. Each nuclear detonation would scatter radioactive fallout. If you launched from Earth's surface, which the early designs proposed, you'd be spreading plutonium and fission products across the atmosphere. The environmental and health consequences would be catastrophic. Second, there was politics. In 1963, the Partial Nuclear Test Ban Treaty prohibited nuclear explosions in space. Orion, which required thousands of bombs, became illegal overnight. The project was shelved. The dreamers moved on. But the idea didn't die. In 1973, the British Interplanetary Society picked up the thread and started working on a new design. They called it Project Daedalus, and it was explicitly designed to reach another star, not just any star, Barnard's star about 6 light-years away. But the principles would work for Alpha Centauri too. Daedalus abandoned nuclear fission bombs in favor of nuclear fusion. Instead of splitting atoms, you'd fuse them. Specifically, you'd use pellets of deuterium and helium, 3 compressed and ignited by electron beams in a reaction chamber at the back of the ship. The fusion reactions would produce thrust, accelerating the spacecraft without the fallout and political baggage of fission bombs. The designers worked on Daedalus for 5 years, publishing their final report in 1978. The spacecraft they proposed was enormous, 54,000 tons at launch, most of it fuel. It would be a 2-stage vehicle like the Saturn V rocket that sent astronauts to the moon, except vastly larger. The first stage would burn for 2.05 years, accelerating the ship to about 7.1% the speed of light. Then, it would detach and fall away, and the second stage would ignite burning for another 1.76 years, and accelerating the ship to 12% the speed of light. At that speed, Daedalus could reach Barnard's star in about 46 years. Alpha Centauri being closer would take roughly 36 years, still too long for a human crew unless you solve the problem of life support radiation, shielding, and psychological endurance, but short enough that you could send a robotic probe and potentially get data back within a human lifetime. Launch it when you're 20. Receive the first images when you're 60. Old but alive, still able to see the fruit of the mission. But Daedalus had its own problems. The biggest was fuel. Helium-3 is extremely rare on Earth. There's a bit in the upper atmosphere, a bit embedded in lunar regolith from billions of years of solar wind bombardment, but nowhere near enough to fuel a 54,000-ton spacecraft. The designers proposed mining helium-3 from the atmosphere of Jupiter, which has vast quantities. But that introduces another impossibly difficult engineering challenge. How do you scoop gas from a planet with gravity so strong it would crush most spacecraft in an atmosphere with winds faster than anything on Earth, and then transport thousands of tons of it back to wherever you're building the ship? The whole project assumed technologies we didn't have, resources we couldn't access, and infrastructure we hadn't built. It was a beautiful dream, rigorous, detailed, completely impractical. Around the same time, another idea was circulating. The Ensman starship proposed by Dr. Robert Ensman in 1964. This one took a different approach. Instead of trying to go fast, focus on going far. Build a ship so massive, so self-sufficient, that it doesn't matter if the journey takes centuries. Ensman's design called for a huge ball of frozen deuterium, 12 million tons of it, serving as both fuel and radiation shielding. Attached to this icy sphere would be 3 cylindrical habitats, slowly rotating to create artificial gravity. The ship would use nuclear pulse propulsion, similar to Orion, accelerating slowly but steadily over decades until it reached a cruising speed. The journey to Alpha Centauri would take about 60 years at 9%, the speed of light, assuming everything worked perfectly. But Ensman didn't design it for a single crew. He designed it as a generation ship, a vessel where the people who launched would die long before arrival. Their children would grow up in space, live their entire lives aboard the ship, have children of their own, and die. And their children's children would finally see Alpha Centauri, a multi-generational exodus, a bet that human society could remain stable, cohesive, and functional for decades or centuries in a closed environment with no possibility of resupply, no escape, no turning back. There's something deeply unsettling about generation ships, isn't there? You're asking people to sacrifice not just their own lives, but the lives of their descendants for a goal none of them will achieve. The first generation might volunteer willingly, driven by the romance of exploration. But what about the second generation, the ones born in space who never chose this life? They didn't ask to spend their entire existence in a metal tube hurtling through the void. Do they have the right to turn around, to mutiny, to say no? We're done. We want to go home, even though home is now light years behind them. And unreachable scientists have studied the psychology of long duration spaceflight, and the results are not encouraging. Even on the International Space Station, where astronauts spend only 6 months to a year and can see Earth outside the window and communicate with family in real time, people struggle. Isolation, confinement, monotony. The constant background stress of knowing that any mistake could be fatal. It wears on you. Now imagine that for 60 years, or 80, or 100. No Earth, no rescue, no end in sight except a destination you'll never live to see. Research shows that humans are not psychologically built for isolation on that scale. We're social creatures. We need variety, novelty, connection to nature. We need the feeling that our actions matter, that our lives have purpose beyond simple survival. A generation ship would need to provide all of that artificially. Gardens, recreation, art, culture, some sense of community and meaning. But how do you maintain culture when you're cut off from the civilization that created it? When there are no new books, no new music, no new ideas flowing in from the outside world, you'd be living in a time capsule culturally frozen while Earth continues to evolve without you. And by the time you arrive at Alpha Centauri, if you arrive, you might be so different from the humans who sent you that you're barely recognizable. There's another problem: radiation, cosmic rays, high-energy particles from supernovae and other violent cosmic events. On Earth, we're protected by a magnetic field and a thick atmosphere. In space, you're exposed. A generation ship would need shielding, lots of it. Water ice or dense materials like lead. But shielding is heavy, which means more mass, which means more fuel, which means a bigger ship, which compounds every other problem. One proposed solution was to simply accept the radiation exposure and adapt. Use genetic engineering to make humans more resistant to DNA damage, or put the crew in cryogenic sleep for most of the journey, waking them only when necessary. But cryonics is still science fiction. We can freeze cells, embryos, small organisms. But a whole human body, we don't know how to freeze someone without ice crystals forming and shredding cell membranes. We don't know how to revive them without catastrophic damage. It's a technology that might exist someday. Might. But betting a multi-trillion-dollar mission on it seems reckless. Here's the uncomfortable truth that all these proposals eventually confronted. Interstellar travel isn't just an engineering problem. It's a biological problem, a psychological problem, a sociological problem. You can design the perfect ship, solve the propulsion, solve the energy, solve the navigation. And you'd still have to deal with the fact that the passengers are human, fragile, mortal, prone to conflict and despair and doubt. And there's no patch for that. No firmware update that fixes the human condition. So, why did people keep proposing these missions? Why did brilliant scientists and engineers spend years designing ships they knew would probably never be built? Was it hope, stubbornness, a refusal to accept limits? Or maybe it was something else. Maybe it was the recognition that the act of dreaming of imagining the impossible pushes us to develop the technologies and ideas that eventually become possible. Orion led to research in nuclear propulsion that influenced later spacecraft designs. Daedalus deepened our understanding of fusion physics. Ensman forced us to think seriously about closed-loop life support systems, the kind we now use on the ISS. None of these ships were built, but they weren't failures either. They were stepping stones, sketches on the path towards something we don't yet understand. Do you think it's worth it? Spending decades, centuries, even designing ships that might never fly? Or is there value in the dreaming itself, in the refusal to let distance be the final word? Because the alternative is acceptance, the acknowledgement that some places are simply beyond reach, that Alpha Centauri, our nearest neighbor, might remain forever untouched by human hands. And maybe that's okay. Maybe wonder doesn't require conquest. But humans have never been good at leaving things alone, especially things that seem just barely out of reach, taunting us with their proximity. Imagine a spacecraft the size of a postage stamp, weighing less than a paperclip, accelerated to 20% the speed of light by a laser so powerful it could be seen from other star systems. No fuel, no nuclear bombs, no massive engines. Just light pure and focused, pushing a tiny reflective sail across the void. It sounds like fantasy, like something from a novel written by someone who doesn't understand physics. But in April 2016, three of the most credible names in science stood together and announced they were going to try it. Stephen Hawking, Yuri Milner, and Mark Zuckerberg. And they called it Breakthrough Starshot. The announcement was met with equal parts excitement and skepticism. Could it work? Could you really send something to Alpha Centauri using nothing but focused light? Or was this just billionaire vanity, a high-profile stunt designed to generate headlines and fade into obscurity when the engineering realities became clear? The core concept of Breakthrough Starshot is deceptively simple. Light carries momentum. When photons hit a surface, they transfer a tiny amount of force. It's the principle behind solar sails, which have already been tested in space. The Japanese spacecraft Icaros, launched in 2010, successfully demonstrated interplanetary travel using a solar sail. It unfurled a thin reflective sheet and let sunlight push it toward Venus. Slow, gentle, but real, measurable, functional. Breakthrough. Starshot takes that concept and amplifies it to an extreme. Instead of relying on the diffuse light of the sun, you build an array of ground-based lasers, powerful lasers. Combined, they generate about 100 gigawatts of focused light. That's roughly the output of 100 nuclear power plants, all concentrated into a beam narrow enough to hit a sail the size of a few meters across. The sail would be made of an ultra-lightweight material, possibly a nano-fabricated metamaterial, reflective enough to bounce almost all the laser light and thin enough that the entire spacecraft sail and payload combined weighs only a few grams. You'd launch thousands of these tiny craft, maybe tens of thousands, because some would fail, some would drift off course, some would be destroyed by micrometeorites or cosmic dust. But the ones that survive would be accelerated to 60,000 kilometers per second, 20% the speed of light, in a matter of minutes. Research shows that at 20% light speed, a star chip, as the project calls, the tiny probes could reach Alpha Centauri in about 20 years. Add another 4.37 years for the radio signals to travel back to Earth, and you're looking at a total mission time of roughly 24 to 25 years from launch to first data received. That's within a human lifespan. If you're 30 when the mission launches, you'd be 54 or 55 when the first images arrive. Old enough to have gray hair and aching joints, but young enough to understand what you're seeing. Young enough to feel the weight of it, that we did it. That we sent something to another star and it survived. But the phrase, if it survives, is doing a lot of work there. Because the engineering challenges of Breakthrough Starshot aren't just difficult, they're borderline absurd. Let's start with the laser, 100 gigawatts. For context, the entire United States uses about 450 gigawatts of electricity at peak demand. You'd be using more than a fifth of the country's power output, concentrated into a single laser array firing continuously for several minutes to accelerate each probe. The cost of building such a laser is estimated to be in the tens of billions of dollars, maybe more, and you'd need to fire it thousands of times if you're sending multiple probes. Then there's the problem of focusing. The laser array would likely be located in a high-altitude desert somewhere with clear skies and minimal atmospheric distortion. But even in the best conditions, Earth's atmosphere scatters and absorbs light. You'd lose efficiency. The beam would spread. By the time it reaches the sail, which would already be hundreds or thousands of kilometers away, the intensity would have dropped significantly. You'd need adaptive optics, real-time corrections for atmospheric turbulence, precision targeting systems that can track a sail moving at thousands of kilometers per second and adjust the laser aim on the fly. And the sail itself, it needs to be incredibly thin. We're talking about materials measured in nanometers, thinner than a human hair by orders of magnitude. But it also needs to be strong enough to withstand the initial acceleration without tearing. When the laser first hits the sail, experiences enormous stress. The force isn't distributed evenly. Hotspots can form places where the laser intensity is slightly higher, and those spots can burn through the material in microseconds. Scientists suggest that the sail would need to be made of something like graphene or a specially engineered metamaterial that can reflect the laser light almost perfectly and dissipate heat faster than it accumulates. We don't have materials like that yet. Not at the scale required, not with the properties needed. Let's say you solve the laser problem and the sail problem. The probe accelerates successfully and reaches 20% the speed of light. Now it's coasting, no more propulsion, just momentum carrying it forward through the interstellar medium. And here's where things get dangerous. Space is not empty. It's close to empty, yes, but there are still atoms, hydrogen mostly. About 1 atom per cubic centimeter in interstellar space. That doesn't sound like much. And at normal speeds, it isn't. Voyager 1 has been traveling through interstellar space for years without issue. But Voyager is moving at about 17 kilometers per second. The Starship would be moving at 60,000 kilometers per second. At that speed, even a single hydrogen atom becomes a high-energy particle. When it hits the spacecraft, it doesn't just bounce off. It impacts with the force of a cosmic ray. Scientists estimate that a starship traveling at 20% light speed would be bombarded by trillions of hydrogen atoms over the course of the journey, each one transferring energy, each one potentially damaging the delicate electronics. The sail itself might survive, it's just reflective material. But the payload is another story. The payload contains cameras, sensors, communication equipment, power systems. All of it packed into a space smaller than a coin. All of it has to survive 20 years of relentless atomic bombardment. And then there's dust. Interstellar dust grains, tiny particles of carbon silicates ice. They're rare, but they exist. If a dust grain the size of a grain of sand hits the starship at 60,000 kilometers per second, the kinetic energy would be equivalent to a small explosion. The spacecraft would be obliterated, instantly. No warning, no chance to evade, just gone. There's no way to shield against that. Not at these speeds, not with the mass constraints. The only option is to accept the risk. Launch thousands of probes and hope that, statistically, some of them make it through. It's a numbers game. A bet that the vastness of space, the emptiness between the dust grains, will be kind to at least a few of the craft. Let's say a probe survives, 20 years pass. It's approaching Alpha Centauri, screaming through the system at 20% the speed of light. How long does it have to collect data? At that speed, it crosses the distance from the Sun to Earth in about 8 minutes. The entire Alpha Centauri system from Proxima out to the binary pair in maybe a few hours. You get one shot, one pass. The cameras need to be pointed correctly, the instruments need to activate at exactly the right time. The data needs to be recorded and then transmitted back to Earth across 4 light years using a communication system powered by whatever energy source the probe carries, which can't be much because the whole thing weighs a few grams. The communication challenge alone is staggering. To send a signal strong enough to be detected on Earth from 4 light years away, you need a powerful transmitter. But power requires energy, and energy requires mass, either in the form of batteries or solar panels, or some kind of radioisotope thermoelectric generator, all of which add weight, all of which make the initial acceleration harder. Research shows that even with optimistic assumptions, the data rate from a star chip would be incredibly low, maybe a few bits per second. It would take hours, days even to transmit a single image. And the probe only has a short window to transmit before it flies out of the system and loses line of sight with Earth. You'd have to prioritize. What do you send? First, a photo of Proxima b spectroscopic data of the atmosphere measurements of the magnetic field. You can't send everything. You have to choose. And you have to choose correctly because there's no second chance. Then there's the question of slowing down. Breakthrough? Starshot doesn't have a plan for that. The probes are designed to fly through the system at full speed, collect what data they can, and keep going. They'll drift into the dark beyond Alpha Centauri, eventually leaving the galaxy entirely over millions of years. One-way missions. Scouts that never return. Some scientists have proposed modifications. Maybe you could detach part of the sail and use it to catch light from Alpha Centauri itself, using the star's photons to decelerate. But that requires precise maneuvering additional mass and a sail that can withstand being flipped around while still traveling at relativistic speeds. It's technically possible, maybe, but it compounds the difficulty. And then there's cost. The initial estimates for breakthrough Starshot were around $5 to $10 billion. That's just for the laser array and the first batch of probes. It doesn't include the decades of research and development needed to create the sails, the miniaturized payloads, the communication systems. It doesn't include the cost of running the laser, maintaining the facility, training the personnel. By the time you factor in everything, you're probably looking at tens of billions, possibly more, for a mission that might not work. That might send back a few grainy images and some fragmentary data, if you're lucky. Is it worth it? That's the question people keep asking. Is the scientific return worth the investment? We could use that money to build more telescopes, send more missions within our solar system, study Mars and Europa and Enceladus up close. Places we can actually reach with current technology. Places where we might find life without needing to invent entire new fields of engineering. But there's a counter-argument, a philosophical one. Alpha Centauri is the closest star. If we can't send something there, if we can't even manage that, then interstellar travel isn't just difficult, it's impossible. And that has implications. It means the stars are forever out of reach. It means humanity is confined to this one solar system for the rest of our existence, however long that lasts. And maybe that's fine. Maybe there's enough to explore here, enough mysteries within a few astronomical units of home. But it closes a door, permanently. And once a door is closed, once a generation decides something is too hard and gives up, it's very difficult to open it again. Breakthrough Starshot is still in the research phase. The lasers haven't been built. The sails are still in development. The mission is years, maybe decades away from an actual launch. And there's a very real possibility it will never happen, that the funding will dry up, that the technical challenges will prove insurmountable, that the project will join the long list of ambitious interstellar proposals that sounded brilliant on paper and died quietly in the planning stages. But maybe that's not the point. Maybe the value isn't in the mission itself, but in what we learn trying to build it. The materials research, the laser technology, the miniaturization of electronics, These are technologies that have applications far beyond sending tiny spacecraft to Alpha Centauri. They push the boundaries of what's possible. They force us to think differently, to solve problems we didn't even know existed. And whether or not we ever reach another star, that process, that relentless pushing against the limits, is what drives progress. What makes us more than we were? Still knowing all that, understanding the science and the engineering and the sheer improbability of success. There's something almost heartbreaking about it, isn't there? The idea that we could build something capable of touching another star, and the only thing stopping us is us. Our limitations, our biology, our brief, fragile lives. Let's say we solve it. Let's say breakthrough starshot works, or some other technology emerges, and we finally have the ability to send not just a probe, but a human being to Alpha Centauri. You volunteer, you're young, healthy, brilliant. You've trained for years, and one day you climb aboard a spacecraft, the doors seal behind you, and you begin a journey that will last decades. By the time you arrive, everyone you've ever known will be old or dead. The world you left will have moved on without you, and you'll step out onto a planet 4 light years from home, knowing you can never go back. Would you do it? Would anyone? Interstellar travel isn't just a physics problem or an engineering challenge. It's a human problem, and humans are messy. We're fragile in ways that have nothing to do with cosmic rays or micrometeorites. We break psychologically, we lose hope, we forget why we started, and no amount of advanced propulsion or shielding can fix that. Let's start with the body. Research shows that human beings are exquisitely adapted to life on Earth. We evolved under 1 g of gravity. Our bones are strong enough to support our weight, but light enough that we can move efficiently. Our cardiovascular system is tuned to pump blood against gravity up to the brain, down to the feet. Our inner ears are calibrated to detect acceleration and maintain balance in a gravitational field. Take gravity away, and everything starts to fall apart. Astronauts on the International Space Station lose about 1 to 2% of their bone mass per month. That might not sound like much, but over a year, it adds up. Over 5 years, 10 years, 20 years, you'd be looking at catastrophic bone loss. Your skeleton would become brittle, porous, fragile as chalk. A simple fall could shatter your femur. A hard sneeze could crack a rib. Muscles atrophy even faster. Without gravity to work against your muscles, don't need to be strong. They weaken, shrink. Astronauts on the ISS exercise for 2 hours a day on specialized equipment just to slow the process, and even then, they come back weaker than they left. On a multi-decade journey to Alpha Centauri, no amount of exercise would fully compensate. You'd arrive as a shadow of yourself, thin, weak, barely able to stand under even the modest gravity of Proxima b, if it has gravity at all. And that's just the mechanical damage. There's also radiation. We have touched on this before, but it bears repeating. Earth's magnetic field shields us from most cosmic rays. The atmosphere absorbs the rest. In space, you're exposed. Every high-energy particle that passes through your body has a chance to damage DNA. Most of the time, your cells repair the damage. But sometimes they don't. Sometimes the repair goes wrong, and a mutation occurs. And mutations accumulate. Over years, over decades, the risk of cancer climbs exponentially. Scientists estimate that on a mission to Mars, which would take about 6 to 9 months each way, astronauts would be exposed to radiation levels that increase their lifetime cancer risk by about 5%. For a journey to Alpha Centauri, even with shielding, even with the best technology we can imagine, the radiation exposure would be orders of magnitude higher. You'd be lucky to survive the trip without developing multiple cancers. Then there's the cardiovascular system. In microgravity, your heart doesn't have to work as hard. It atrophies like any other muscle. Blood redistributes toward your upper body, your face puffs up, your legs thin out. Over time, your heart becomes weaker, less efficient. And when you finally arrive at your destination and gravity returns, your heart might not be able to handle it. You could experience orthostatic intolerance, where standing up causes a dangerous drop in blood pressure, fainting, dizziness. In severe cases, cardiac arrest. Your eyes change too. Astronauts on long-duration missions often report vision problems. The fluid in their bodies shifts in microgravity, increasing pressure inside the skull, which can flatten the eyeball and damage the optic nerve. It's called spaceflight-associated neuroocular syndrome, and it's not fully understood. Some astronauts recover, some don't. On a 20-year journey, the damage could be permanent. You might arrive at Alpha Centauri blind, but physical damage is only part of the equation. The psychological toll is harder to quantify, but potentially more devastating. Imagine being sealed inside a metal tube with the same small group of people for 20 years. No privacy, no escape. Every argument, every personality clash. Every moment of frustration or boredom or despair you have to endure because there's nowhere else to go. You can't quit. You can't take a vacation. You can't even step outside for fresh air. There is no outside, just the interior of the ship, and beyond that, the void. Research shows that isolation and confinement lead to predictable psychological effects: depression, anxiety, irritability, sleep disturbances, cognitive decline. The longer the confinement, the worse the symptoms. On submarines, which are probably the closest analog we have to long-duration spaceflight crews, are carefully selected and rotated every few months to prevent psychological breakdown. But you can't rotate a crew on an interstellar mission. You can't bring in fresh people. You're stuck with whoever launched with you for better or worse until the end. And communication with Earth doesn't help much. Because of the distance, every message you send takes years to reach home. Every reply takes years to come back. You could send a distress signal, a cry for help, and by the time anyone on Earth hears it, you could be long dead. There's no mission control offering real-time guidance, no ground team troubleshooting your problems. You're on your own, truly, absolutely alone. Scientists suggest that one way to mitigate the psychological stress would be to use cryogenic sleep. Freeze the crew for most of the journey, wake them only when necessary. But as we discussed earlier, cryonics is still theoretical. We don't know how to freeze a human being without killing them. And even if we did, there's a deeper question. If you're frozen unconscious for 20 years, are you really making the journey? Or are you just skipping it, blinking out of existence and reappearing decades later with no memory of the time in between? Is that even the same person who left Earth? Or is it a copy, a version of you that lost 20 years and has to live with the consequences? There's another approach: generation ships. Ships where the crew lives, reproduces, and dies during the journey, passing the mission on to their children. But that raises even darker questions. The first generation, the ones who volunteer, presumably understand what they're signing up for. They know they'll never see Earth again. They've made peace with it. But what about their children, the ones born in space who never chose this life? They didn't ask to spend their entire existence in a confined environment, hurtling toward a destination they'll never see. Do they have the right to turn around to say, no, this wasn't our choice, we want to go home? And what is home to them? Earth is just a story, a place their parents talk about, maybe some videos and recordings, but not real, not tangible. The ship is home, the only home they've ever known. And the idea of arriving at Alpha Centauri, of stepping onto a planet they've never seen, might be terrifying. Alien, wrong. Research shows that humans need connection to nature. We need open skies, sunlight, the smell of rain, the feeling of wind. Deprive someone of those things for long enough, and they start to deteriorate mentally. Biosphere 2. The experimental sealed environment in Arizona in the early 1990s was supposed to demonstrate that humans could live in a closed ecosystem. It failed. The participants experienced severe psychological stress conflicts, depression. And that was only for 2 years on Earth, where they could see the outside world through the glass and knew they could leave if necessary. Imagine the same situation, but in space with no possibility of escape for generations. There's also the question of culture. A generation ship would be culturally isolated. No new books, no new music, no new ideas flowing in from Earth. Well, there would be, but delayed by years. By the time a new cultural movement reaches the ship, it's already old news back home. The crew would be living in a time capsule culturally frozen while Earth continues to evolve. And by the time they arrive at Alpha Centauri, if they arrive, they might be so different from the society that sent them that they are unrecognizable. A separate civilization, a new branch of humanity shaped by decades of isolation and hardship. Would they even want to stay in contact with Earth? Or would they drift away, develop their own language, their own traditions, their own identity until Earth becomes a myth, a distant memory, something that happened long ago to people they never knew? And here's the cruelest irony. Let's say the first generation ship launches in, say, 2050. It travels at 10% the speed of light. The journey to Alpha Centauri takes 43 years. But technology keeps improving. In 2070, someone invents a faster propulsion system. A new ship launches traveling at 20% the speed of light. It reaches Alpha Centauri in 21 years. It arrives before the first ship. The original crew who sacrificed everything, who spent decades in transit, arrived to find that they've been beaten, that their mission was obsolete before they even got there, that younger, faster ships overtook them while they were still crawling through the void. Would that break them, knowing that their sacrifice was pointless? That they could have waited, stayed on Earth, lived normal lives, and the mission would have happened anyway without them. There's a term for this: the weight calculation. It's a variation of the interstellar travel paradox. If technology keeps improving, there's always a temptation to wait for the next generation of propulsion, the next breakthrough, because launching now means committing to outdated technology. But if everyone waits, no one ever launches, and the mission never happens. So, when do you decide that the technology is good enough, that the risk is acceptable, that the time is now? Because every year you wait, people age, opportunities close, and the window for action narrows. Do you think humans are psychologically capable of interstellar travel? Not in the abstract, not as a species, but as individuals. Could you personally handle 20 years in a metal tube? Could you watch your body deteriorate, your mind fracture, your connections to Earth fade into silence? Could you accept that you might die before arrival, that all your suffering might be for nothing? Or maybe the question isn't whether we're capable. Maybe it's whether we should be, whether some things are better left as dreams. Because the cost of interstellar travel isn't just measured in dollars or decades. It's measured in human lives, in sanity, in the slow erosion of everything that makes us who we are. And maybe the stars aren't meant to be reached. Maybe they're meant to be admired from a distance. Beautiful, distant, forever out of reach. But that thought, that quiet acceptance of limits, feels like giving up. And humans have never been very good at that. So we keep planning, keep calculating, keep imagining the impossible, even as the evidence mounts that we're simply not built for the journey we dream of taking. Every clear night in the southern hemisphere, Alpha Centauri rises, quietly, predictably. It's been doing this for billions of years, long before humans existed, and it will continue long after we're gone. 2 golden stars and 1 dim red companion, locked in their ancient dance, indifferent to whether anyone is watching. And maybe that's the most humbling thing about all of this. We've spent centuries studying Alpha Centauri, dreaming about it, designing impossible ships to reach it. And it doesn't care. It simply exists, burning hydrogen into helium, pulling on its companions with invisible threads of gravity, shining with the steady patience of something that has all the time in the world. We've traveled a long way together through this story, from the first observations by ancient astronomers who saw a single bright point and had no idea what they were looking at, to Thomas Henderson's sweating over measurements in 1833, calculating a distance so vast It redefined our understanding of space. From Robert Innes discovering Proxima in 1915, the closest star we'd missed for all of human history, to the Pale Red Dot campaign in 2016, finding planets we'll probably never visit orbiting a star we can barely see. We've watched engineers dream up nuclear pulse ships and fusion rockets light sails, and generation ships each designed more ambitious and more impossible than the last. We've done the math, calculated the energy requirements, confronted the brutal reality that 4 light-years might as well be 4 million when measured against human capabilities. And we've asked the hardest question. Not whether we can reach Alpha Centauri, but whether we should. Whether the cost in human terms, the isolation and radiation, and slow psychological erosion is worth the destination. And the answer quietly, devastatingly is probably no. We're not going to Alpha Centauri, not in our lifetimes, maybe not ever. That's not pessimism, it's realism. The distances are too great, the speeds required are too high, the energy costs are astronomical, literally. And the human body, fragile and evolved for one specific planet under one specific star, is simply not built for journeys measured in decades through the void. But here's the strange thing. Knowing that accepting it doesn't make Alpha Centauri less interesting. It makes it more precious. Because distance impossibility, the knowledge that we'll probably never touch something, gives it a kind of weight, a significance that easy things lack. Think about it. If Alpha Centauri were easy to reach, if we could hop on a spacecraft and be there in a few weeks, we probably would have done it already. Built resorts, mined the asteroids, turned it into just another destination, mundane and commercial. The mystery would be gone. The wonder would fade. It would become background noise, something we take for granted like air travel or the internet. Miraculous technologies that we've stopped noticing because they're everywhere. But Alpha Centauri resists us. It sits there close enough that we can study it in detail, far enough that it remains untouchable. And that distance preserves something, a sense of awe, a reminder that the universe is larger than our ambitions, that not everything bends to human will, that some things are simply beyond us, and maybe that's okay. Research shows that humans need unreachable goals. We need horizons we can't quite cross. Because the act of striving, of reaching towards something we might never achieve, is what drives progress. The Apollo program didn't just put people on the moon. It created technologies that transformed telecommunications, materials, science, medicine, computing. GPS, MRI machines, water purification systems, thousands of innovations that emerged from the effort to do something absurdly difficult. The goal justified the journey, even if the goal itself was symbolic. Alpha Centauri serves the same purpose. We probably won't send humans there, but the attempt to imagine how we might, the engineering challenges, the physics problems, the materials, research, all of it pushes us forward. Breakthrough Starshot. Even if it never launches a single probe, is advancing laser technology, nanomaterials, photonics, fields that will have applications far beyond interstellar travel. The dreamers who designed Project Orion and Daedalus weren't wasting their time. They were exploring the boundaries of the possible, and those boundaries once mapped become starting points for the next generation. Maybe that's the real lesson of Alpha Centauri. It's not a destination, it's a direction. A point on the horizon that we aim for, knowing we might never arrive, but understanding that the aiming itself changes us, makes us smarter, more capable, more aware of our place in a universe that doesn't revolve around us. There's a concept in philosophy called the sublime. It's the feeling you get when you encounter something so vast, so overwhelming, that it exceeds your ability to comprehend it. Standing at the edge of the Grand Canyon, watching a thunderstorm roll across the plains, looking up at the night sky and realizing that every point of light is a sun, many of them larger and brighter than ours, and the distances between them are so great that light itself, the fastest thing in the universe, takes years or centuries or millennia to cross the gaps. The sublime isn't comfortable. It's not peaceful. It's unsettling, humbling, a little frightening. Because it reminds you how small you are, how brief, how utterly insignificant in the grand scheme of things. And yet, there's a strange comfort in that too. Because if you're insignificant, then your mistakes don't matter as much. Your failures aren't catastrophic. The universe will continue with or without you. The stars will keep burning. Alpha Centauri will keep shining. And that takes the pressure off in a way. You don't have to solve everything. You don't have to reach every goal. You just have to try. And even if you fail, even if every attempt to cross those 4 light years ends in disappointment, the trying is enough. The dream is enough. Some people find that thought depressing. The idea that we're stuck here confined to our tiny corner of the galaxy, unable to reach even our closest neighbors. But I don't see it that way. I see it as a gift. Because Earth, this one fragile planet spinning around an ordinary star, is all we have. And knowing we can't easily leave, can't start over somewhere else, makes it more valuable, more worth protecting. We live in a time when it's easy to feel hopeless. Climate change, political instability, the creeping sense that things are getting worse and there's nothing we can do about it. But look at what we've accomplished in just a few centuries. We've gone from not knowing the distance to the nearest star to measuring it with absurd precision. We've discovered planets around that star. We've designed ships, however impractical, that could theoretically reach it. We've sent machines to the edge of the solar system and beyond. Voyager 1, launched in 1977 with technology less powerful than a modern smartphone, is still out there, still transmitting 15 billion miles away and counting. We did that. Fragile, short-lived humans with brains that evolved to hunt gazelles and gather berries. We looked up, wondered, and built machines that could touch the stars, even if we couldn't. That's not nothing. That's extraordinary. And maybe someday we'll figure it out. Some future generation equipped with technologies we can't even imagine will crack the problem of interstellar travel. They'll build ships that can reach Alpha Centauri in years instead of decades. They'll develop medical treatments that counteract bone loss and radiation damage. They'll solve the psychological challenges of long-duration isolation. And they'll go. Not because it's easy, but because it's hard. Because the human drive to explore, to push boundaries, to see what's over the next hill is stronger than the obstacles in the way. Or maybe they won't. Maybe they'll look at the distances, the costs, the risks, and decide it's not worth it. That there are better ways to spend resources. That virtual reality or AI or some technology we haven't invented yet will make physical travel obsolete. That experiencing the universe through data and simulations is enough, and the dream of stepping foot on another world orbiting another star is a relic of a more naive time. I don't know which future we're heading toward. Nobody does, but I know this. Right now, tonight, Alpha Centauri is out there, 4.37 light years away, close enough to study, too far to touch. And the light that's entering your eyes, if you're lucky enough to see it, left that star over 4 years ago. It traveled through the void patient and constant just to reach you. A photon that began its journey when the world was different, when you were younger or maybe not even born yet. And it arrived at this exact moment, this exact second, to deliver an image of a star, as it was not as it is. That's worth something, isn't it? The idea that the universe is still sending us messages, still showing us beauty even if we can't respond in kind. Even if all we can do is look and wonder and dream. So maybe we never reach Alpha Centauri. Maybe it stays forever out of reach, a beautiful impossibility, a reminder of our limits. But we'll keep looking, keep measuring, keep designing ships that will never fly and dreaming dreams that will never come true. Because that's what we do. That's what it means to be human, to reach for things we can't have, to strive for goals we'll never achieve, and to find meaning not in the arrival, but in the reaching. Alpha Centauri doesn't need us. It doesn't need our attention or our ambition. It will shine whether we're here or not. But we need it. We need something to aim for, something vast and distant and impossible, something that reminds us that the universe is bigger than our problems, older than our civilizations, more patient than our lifetimes. And as long as it's there glowing quietly in the southern sky, we'll have a direction, a purpose, a reason to keep looking up. Sleep well, dreamer. And when you wake, if the sky is clear and you happen to be in the right hemisphere, look south. Find the constellation Centaurus, and there nestled among the stars is Alpha Centauri, two golden points of light so close they almost touch, and a third you can't see hiding in the dark, our nearest neighbors, our impossible dream. A reminder that some distances aren't meant to be crossed, only admired, only wondered at, only felt. Thank you for drifting through this story with me, for listening to the quiet tale of a star that's both impossibly close and forever far. The universe is full of mysteries, full of stories waiting to be told softly in the dark. And if you'd like to hear more, stay close. There are other stars, other worlds, other impossibilities to explore. But for now, rest, dream gently, and let the stars do what they do best. Shine patiently in the distance, waiting for no one, witnessed by all who choose to look. Good night.